When astronomers first began to understand that galaxies are rotating systems, one simple expectation would have seemed reasonable. If gravity pulls matter together and rotation spreads that matter out into a disk, then perhaps a mature galaxy should end up looking broad, flat, and mostly smooth. A little brighter near the center, a little thinner toward the edge, but still fairly even overall. That sounds like a sensible starting point. It just is not what the sky gives us. Again and again, when we look at nearby disk galaxies, we do not see smooth circular sheets of stars. We see structure. We see curved arms, dark dust lanes, bright blue clusters, glowing star-forming regions, bars crossing the center, and outer disks that look far more organized than a simple rotating blur should. By the time Edwin Hubble formalized his galaxy classification scheme in the 1920s, spiral galaxies had already made the problem impossible to ignore. A rotating disk was not staying visually bland. Something inside the disk was shaping matter into pattern. That is where the first real step begins. A galaxy is not made of one ingredient behaving in one way. It is a mixed system. Stars move on long orbits and usually pass one another without collision. Gas clouds can compress, cool, fragment, and collapse. Dust absorbs light and marks out denser lanes inside the disk. The central bulge often contains older stars, while the disk contains more gas and many younger populations. Once those ingredients are placed inside one rotating gravitational system, the expectation of smoothness becomes much weaker. That is easy to miss because the word disk sounds simple. It makes the galaxy sound like a finished shape. But in practice, a disk is not a final answer. It is a setting where new differences can grow. A slightly denser region can pull a bit more strongly on nearby material. A passing gas cloud can be compressed as it enters that region. Once gas is compressed, star formation becomes more likely. Once young stars appear, that region becomes easier to see. So the galaxy does not merely rotate. It develops contrast. This is one reason telescope images matter so much here. They did not merely make galaxies look beautiful. They showed that the light is not spread evenly. In face-on spirals such as Messier 74, the arms are easy to trace, and the blue knots of young stars make the pattern visible across the disk. In edge-on systems such as NGC 5866, a dark dust lane cuts through the galaxy and reveals that the disk itself has internal structure, not just overall shape. These observations pushed astronomy beyond classification. They forced a harder question. Why should a rotating disk organize itself this way at all? A useful point in the history of the subject is that astronomers learned to classify these shapes before they fully understood them. That happens often in science. First, something is seen clearly enough to sort into categories. Only later does the mechanism become sharp. Spiral galaxies are a good example. The eye could see the arms long before theory could explain why the arms existed, how they lasted, or what part gas, stars, and gravity were each playing. So for a while, the shape was known better than the reason for the shape. That gap matters because it shows where intuition begins to fail. If a person hears the word spiral, it is tempting to think rotation already explains everything. Rotate a system long enough, and perhaps curved patterns simply appear. But that is too vague to count as an explanation. rotation can help flatten matter into a disk. It does not automatically explain why the disk breaks into distinct arms, why dust gathers into narrow lanes, or why some regions are lined with young blue stars while others are not. So the real subject is not just spinning. It is organization inside a spinning system. The Milky Way makes this even more interesting because we do not have the luxury of viewing our own galaxy from the outside. We live inside its dusty disk, about 26,000 light-years from the center, roughly 8 kiloparsecs away. That makes the overall structure much harder to reconstruct. Even so, the conclusion is the same. The galaxy we live in is not a smooth rotating sheet. It has a central bar, spiral structure, dense gas, and star-forming regions distributed unevenly through the disk. So the problem is not limited to a few photogenic galaxies chosen for posters. It includes our own home system. At this stage, it helps to separate three ideas that often get blurred together. Gravity helps gather matter into galaxies. Rotation helps spread some of that matter into disks. But neither of those by itself fully explains why so many disk galaxies grow visible internal patterns. That third step requires extra physics inside the disk itself. It requires matter to respond unevenly, to gather in some regions more than others, and to keep producing visible structure over long spans of time. And once that thought settles in, the arms begin to look different. They are no longer just pretty curves. They are evidence that a galaxy is doing more than rotating. They tell us the disk is active, that gas and stars are not arranged at random, and that internal structure is being maintained or rebuilt by real physical processes. The blue stars in the arms are especially important here because blue stars are young. They do not live very long on galactic timescales. So when we find them tracing spiral arms, the arms cannot be explained only as old, passive features left over from some ancient stage. They are tied to relatively recent activity in the disk. The dark dust lanes matter just as much. Dust is not spread evenly either. It tends to mark denser regions where gas has gathered. Those regions are exactly the places where future stars can form. So a spiral arm is often telling two stories at once. One is about structure, because matter has been organized into a visible lane. The other is about change, because that same lane can become a site of fresh star formation. The arm is therefore not just a boundary in the light. It is part of the working life of the galaxy. By now, the opening mystery has become much clearer. Galaxies are not smooth disks because a disk full of stars, gas, and dust does not remain evenly spread once gravity, motion, density differences, and star formation begin interacting across billions of years. A rotating galaxy is not a calm surface. It is a system where small differences can grow into visible structure. That is why spiral arms appear at all. Not because rotation alone paints them there, but because the disk is physically capable of organizing matter into long-lived patterns. But that first answer creates a harder difficulty almost immediately. A galaxy does not rotate like a solid object. The inner parts move around the center faster than the outer parts. And once that is taken seriously, every long curved arm begins to look mechanically unstable. If the arm were just made of the same material staying together, then differential rotation should keep winding it tighter and tighter. Yet spiral galaxies are still everywhere. That is the point where the next layer begins. If this part has been good company for you, thank you for spending your time here. A like or a soft tap on subscribe is a real source of encouragement for me to keep making these long science journeys. And, if you would like, tell me where you were listening from, what time this found you, and anything you think could be improved. I read those notes with real gratitude. A spiral galaxy looks stable when you first see it. The arms curve outward with such balance that the whole system can seem almost fixed, as if the shape has simply been painted onto the disk and left there for billions of years. But that impression begins to fail the moment rotation is taken seriously. A galaxy does not turn like a compact wheel or a rigid metal plate. The material in the inner disk goes around the center more quickly than material farther out. NASA's overview of the Milky Way gives a useful scale for this kind of motion. Our solar system needs about 240 million years to complete one orbit around the galaxy, and that is only one location within a much larger rotating disk. Once motion varies with radius, any long curved feature made of the same stars and gas should be stretched and wrapped more tightly over time. This difficulty became so central that astronomers gave it a plain, almost mechanical name: the winding problem, sometimes called the winding dilemma. The annual review article by Frank H. Hsu explains that spiral density wave theory was developed in part to reconcile exactly this issue: the fact that material's spiral arms in flattened disk galaxies should not survive for long if they are simply made of the same matter staying together as the galaxy rotates. The logic is direct. If the arm were a permanent chain of the same stars, then the inner part of that chain would lap the outer part again and again. Over enough time, the arm would tighten until the broad, graceful spiral was lost. That is where simple intuition starts giving the wrong answer. Rotation seems at first like the very thing that should create spirals. After all, if matter in a disk moves around a center, curved patterns feel natural. But differential rotation is too efficient. It does not preserve large open spirals. It keeps twisting them. Astronomy Notes summarizes the result in a very concrete way. After only about 500 million years, a material spiral pattern would be wound so tightly that the familiar large-scale structure would largely disappear. Since real spiral galaxies are often many billions of years old, and since the sky still contains many systems with wide, obvious arms, the arms cannot usually be long-lived material features made of the same stars remaining side by side forever. A nearby spiral like Messier 81 makes the problem easier to feel. Hubble's detailed images show a classic grand design pattern: two prominent arms curving out from a bright central region, dark dust lanes threading through them, and strings of star-forming regions marking the arms with fresh activity. If those arms were just permanent streams of the same material, then the galaxy's own rotation should have ruined that geometry long ago. Yet, the pattern remains broad and coherent enough to be one of the clearest spiral systems in the sky. The arm, then, cannot be understood simply as a frozen ribbon of matter. This is why the winding problem matters so much at the beginning of the story. It is not a small technical issue added later by specialists. It is the first place where the visible appearance of a galaxy and the mechanics of orbital motion come into direct conflict. A calm image suggests endurance. The rotation law suggests destruction. Something has to give. Either the arms are short-lived and constantly renewed, or they are patterns that persist even while the individual stars and gas clouds pass through them, or different galaxies sustain their spirals in different ways. Modern reviews of spiral structure make clear that this remains an active area of astrophysics rather than a closed case from the 1960s. The historical response to this tension was one of the major advances in galactic dynamics. Instead of treating spiral arms as permanent material objects, astronomers such as Chia-Chow Lin and Frank H. Hsu developed the idea that the visible spiral can be a wave pattern in the disk. In that picture, the pattern has its own angular behavior, while the stars and gas orbit through it. Kormendy's review at NED summarizes the modern form of that idea very clearly. Global spiral structure is widely interpreted as a density wave whose shape rotates almost rigidly, while the disk material itself rotates differentially and flows through it. That sentence matters because it separates the motion of the pattern from the motion of the material. Once those are no longer assumed to be the same, the winding problem stops being fatal and becomes a clue. An ordinary traffic buildup on a highway is still one of the least misleading ways to picture this. The jam has a recognizable location and shape, but the cars inside it are not fixed members of a permanent convoy. They enter, slow down, compress, and then leave. Astronomy Notes uses almost exactly this comparison for spiral structure. In a galaxy, stars, and especially gas, can pile up in regions of enhanced density, creating an arm-like pattern, even though the material itself keeps moving onward around the center. That does not solve every detail, but it immediately explains why a spiral can remain broad instead of winding into a tight knot made of the same particles. Even that is not the end of the matter, because the field has become more nuanced over time. The same modern reviews that describe density wave theory also note that not all spirals are likely sustained by one single mechanism. Dobbs and Baba's review at NED argues that outside some barred galaxies, many spiral arms may be transient and recurrent features, with unbarred two-armed spirals often linked to tidal interactions and other spirals associated with instabilities in the disk. In other words, the broad solution is not that astronomers replaced one rigid answer with another rigid answer. It is that the winding problem forced them to stop treating visible arms as simple permanent objects. After that, multiple physical pathways became possible. This also helps explain why galaxies with similar overall shapes can still behave differently. Some grand design spirals look unusually clean, with long dominant arms. Others are more patchy or fragmented. Some are closely connected to a central bar. Others may be responding to the gravity of companion galaxies. But all of those cases still inherit the same basic constraint. Differential rotation does not allow astronomers to casually treat the spiral as a long-lived painted stripe of fixed material. Any successful explanation has to respect the fact that the disk is shearing all the time. There is a useful human scale hidden inside this problem as well. Our own solar system has completed only about 20 orbits of the Milky Way since it formed, because one galactic year is about 240 million years. That means even a pattern lasting for only a few rotations could still span a very long interval by human standards, yet remain short-lived compared with the age of the galaxy itself. This is one reason spiral structure can seem permanent to us while still being dynamic on galactic timescales. The arm does not need to be eternal to appear enduring. It only needs to last long enough relative to the much slower rhythm of human observation. Observations continue to test how fixed or how temporary these patterns really are. A good example comes again from Messier 81. A study of resolved stellar populations around one of its grand design arms found no convincing evidence for the age gradients expected from a stationary density wave with a single pattern speed, and instead favored spiral structure influenced by tidal interactions with companion galaxies. That result does not erase density wave ideas from astronomy, but it shows how carefully the problem has to be handled in real systems. The galaxy is telling us that arm persistence may come from more than one mechanism, and that even famous textbook spirals are not always as simple as they look. The puzzle is no longer only why galaxies are not featureless disks. It is why large spiral patterns remain visible in disks where the inner regions outrun the outer ones. The answer cannot be because the same matter stays together forever. Differential rotation rules that out for most spirals. The arms survive because they are better understood as patterns maintained, renewed, amplified, or triggered within the disk, rather than fixed ribbons of matter being carried around unchanged. If the arm is not a permanent object, then what exactly is moving through it, and what exactly stays behind? That is where the next layer begins to show itself. A spiral arm looks solid when you first meet it. The curve is clean. The dust lane holds its edge. Blue star clusters sit along the arc as though they belong to a single permanent structure. That visual impression is powerful, and for a long time it was natural to imagine the arm as a fixed stream of matter, a great river of stars and gas winding through the disk. But once differential rotation is taken seriously, that picture begins to fail. The inner galaxy moves around the center faster than the outer galaxy, so a spiral arm made of the same material staying together would keep winding tighter over time. That mechanical difficulty led astronomers toward one of the most influential ideas in galactic dynamics. The arm may be less like a permanent object and more like a pattern of enhanced density moving through the disk. That shift changed the subject completely. Instead of asking which stars belong to an arm forever, astronomers began asking whether the arm itself could be a wave-like pattern while stars and gas pass through it. Frank H. Shu's review of 6 decades of spiral density wave theory describes the origin of the idea clearly. It grew out of attempts to solve the winding dilemma of material spiral arms. In this framework, the spiral is not treated as a rigid painted stripe attached to one set of stars. It is a large-scale pattern in the disk, one that can organize matter without requiring the same matter to remain locked together for billions of years. The traffic jam comparison became popular because it captures the central point without asking the listener to know the full mathematics. A traffic jam has a recognizable shape and location, but the cars inside it do not remain the same. They enter, slow, compress, and eventually leave. A review, hosted by Ned, notes that Ala Toumre described gas clouds piling up at spiral arms, a little like a traffic jam, and NASA now uses almost the same language in public explanations of spiral structure, saying that stars, gas, and dust pass in and out of the spiral arms, much like cars moving through a jam on a highway. The comparison is not perfect, but it is close enough to carry the main physical idea. The arm can persist as a pattern even though its contents are changing all the time. That does not mean every ingredient behaves the same way. Stars and gas respond differently when they encounter a denser region of the disk. A star is mostly a collisionless object in galactic terms. It follows an orbit shaped by the galaxy's gravitational field, and while its motion can be perturbed by a spiral potential, it does not crash into other stars the way cars interact on a road. Gas is different. Gas clouds can compress, shock, cool, and fragment. That makes spiral arms especially visible in gas-rich disks, because the denser lane is not only a place where matter is concentrated for a time, but also a place where the physical state of that matter can change. This is one reason a spiral arm often appears edged by dark dust and bright blue star-forming regions, rather than looking like a neutral smear of old starlight. Images from Hubble show this separation very clearly. In Messier 51, NASA describes the arms as long lanes of stars and gas laced with dust, and emphasizes that these arms act as star formation factories by compressing hydrogen gas and creating clusters of new stars. In NGC 1672, ESA, Hubble highlights clusters of hot young blue stars along the spiral arms, glowing red hydrogen gas, and dust lanes tracing the denser structure. Those visible ingredients tell an important story. The arm is not merely a bright drawing on top of the disk. It is a place where gas has been gathered strongly enough for new stars to form, while dust outlines the denser lanes and the youngest stars make the pattern stand out against the older stellar background. Once that is in place, the phrase "real object" needs to be handled carefully. A spiral arm is real in the sense that the density enhancement is real, the star formation is real, and the gravitational effects on orbits are real. But it may not be a permanent bundle of the same stars and clouds traveling together as one convoy around the galaxy. That distinction is exactly why the density wave idea mattered so much. It allowed astronomers to say that the arm exists physically without requiring it to be a material object in the simple, everyday sense. The pattern can be long-lived while the membership changes. That is the point where the subject stops being a matter of appearance and becomes a matter of dynamics. The wave picture also introduces a new speed into the story. The stars and gas orbit the galaxy at one set of speeds that vary with radius, but the spiral pattern itself may rotate with a pattern speed of its own. Cormandy's review at NED summarizes the classic idea this way: global spiral structure is interpreted as a density wave that rotates almost rigidly, while the material in the disk rotates differentially and flows through it. That sentence is easy to overlook, but it carries the full solution to the paradox. The arm does not survive by forcing the same matter to stay in place. It survives because the pattern and the material are no longer assumed to be identical things. Even so, modern astronomy does not treat one model as the full answer for every spiral galaxy. Reviews over the last decade have stressed that different galaxies may maintain their arms in different ways. The NED review by Claire Dobbs and Junichi Baba explains that while quasi-stationary density waves are one major theoretical framework, many spiral features may instead be transient and recurrent, or may be strengthened by bars and tidal interactions. So the traffic jam picture is valuable, but it is not a license to flatten the subject into one universal mechanism. Some spirals appear especially compatible with long-lived, large-scale patterns. Others seem to be repeatedly rebuilt by internal instabilities or by gravitational encounters with companion galaxies. That matters because even the most famous textbook spirals do not always behave as neatly as the classic picture would suggest. A study of resolved stellar populations in the Grand Design Spiral Messier 81 found no convincing sign of the simple age gradients expected from a stationary density wave with one pattern speed, and instead favored a strong role for tidal interaction with companion galaxies. Results like that do not remove density wave theory from the field. They show that galaxies are more varied than the cleanest classroom sketch. The broad lesson remains secure. Spiral arms are not usually best understood as frozen material structures. But the exact process that keeps an individual arm visible may differ from one galaxy to another. There is also a deeper reason the arm becomes bright precisely where it does. A density pattern can gather gas into narrower lanes. Gas responds by compressing. Under the right conditions, that compression helps trigger star formation. The brightest blue stars that appear afterward are short-lived by galactic standards, so when observers see them lining the arms, they are seeing evidence that the arm is tied to recent structure building inside the disk, rather than to some ancient fixed decoration. This is why NASA's descriptions of grand design spirals repeatedly connect the arms with young stars and active star-forming regions. The arm is not only a density feature, it is also a place where the galaxy's raw material is being processed. The Milky Way gives the same lesson from a less convenient viewing angle. We do not get the luxury of floating outside our own galaxy and looking down on the full design. We live inside the dusty disk, about 8 kiloparsecs from the center, and have to infer the larger structure from radio maps, stellar surveys, and the distribution of gas and star-forming regions. But the same logic applies here as in external spirals. The arm is meaningful because matter is concentrated there for a time, and because star formation is linked to that concentration, not because the arm is a rigid track carrying one unchanging set of stars forever around the galaxy. Seen this way, the phrase galactic traffic jam is useful not because it makes spiral structures sound ordinary, but because it prevents a more serious misunderstanding. Without it, the eye keeps insisting that the arm must be a permanent object. With it, the eye starts to accept that a galaxy can display large-scale order while its contents remain in motion. That is a major step in understanding spiral structure. The arm is real, but its reality lies in the pattern, the density enhancement, the altered flow of gas, and the burst of new stars that follows. What makes it visible is not permanence of membership. It is persistence of organization. If stars and gas move through an arm rather than living inside it forever, then the blue light along the arm is telling us something precise about timing. It means fresh stars are being born where the gas is compressed most effectively, and many of the brightest ones have not had long to wander far from that birthplace. The arm is therefore not just a structure in space. It is a structure with an age sequence written into it, one that links gas flow, compression, and stellar birth. That next layer is where the arms stop looking merely decorative and start revealing why they shine so strongly across the disk. A spiral arm would not stand out so strongly if it were only a curve in the distribution of old stars. Old stellar populations can fill a disk with a broad yellow-white glow, but they do not usually carve the arm into the sky with the brightness that Hubble images reveal. What makes the arm visually dominant is not only where matter is concentrated, but what happens to gas after it enters that denser lane. The arm becomes bright because it is a place where cold interstellar material is gathered, compressed, and pushed closer to collapse. That process produces new stars, and among those newborn populations are hot, massive, short-lived blue stars whose light makes the arm stand out against the darker disk. This is one of the clearest places where the visible beauty of a galaxy is tied directly to physical mechanism. A density enhancement in the disk does not simply make everything a little brighter. It changes the behavior of the gas. Bruce Elmer-Green's review on star formation in spiral arms explains that gas is generally compressed more strongly than stars in a spiral density wave or shock, and that this stronger compression is why the gaseous component responds so visibly inside the arms. Gas can cool, lose pressure support, fragment into giant cloud complexes, and then form molecular clouds dense enough for stars to appear. The stars already orbiting in the disk mostly continue on altered but collisionless paths. The gas is the ingredient that can be squeezed into something new. That difference between stars and gas is easy to miss when looking at a finished photograph. In an image, the blue knots, the pink nebulae, and the dark dust lanes all seem to belong to one decorative curve. In physical terms, they mark different stages of the same local process. Gas enters the denser spiral environment. Dust outlines the compressed lanes. Hydrogen gas begins glowing, where intense ultraviolet light from young stars ionizes the surrounding material. The hottest young stars, especially the short-lived massive ones, light the arm in blue. So the arm is not bright merely because more matter is present there. It is bright because the matter there has been pushed into a more active state. Hubble observations show this with remarkable consistency. In the barred spiral galaxy NGC 1672, ESA and Hubble describe clusters of hot young blue stars along the spiral arms, hydrogen gas glowing red, and dust lanes edging the structure. In NGC 4535, Hubble highlights young star clusters dotting the arms, with many bright blue groupings enclosed by glowing pink clouds. These are not random color accents. Blue light points to hot, massive, recently formed stars. Pink and red emission mark ionized hydrogen in active star-forming regions. Dust lanes mark the denser gas-rich places where the raw material has collected. The arm shines because multiple stages of stellar birth are piled into the same narrow band of the disk. NASA describes the same pattern in Messier 51, one of the best-known grand design spirals in the sky. Its arms are shown as long lanes of stars and gas laced with dust, and NASA explains that these arms act as star formation factories by compressing hydrogen gas and creating clusters of new stars. That wording matters because it ties visual structure to a causal chain. The arm does not simply host young stars by coincidence. The arm helps create the conditions that make those stars appear there in the first place. Once they form, the brightest among them do not live very long by galactic standards, so they remain close enough to their birth environments to keep tracing the arm in blue. The color itself is telling us something exact about stellar physics. Massive young stars burn much hotter than lower mass stars, and hotter stellar surfaces emit more strongly at shorter wavelengths, giving these stars a blue or blue-white appearance. They are also brief lives on galactic timescales. A star, many times the mass of the Sun, can exhaust its core fuel far faster than a smaller red star. That means a bright blue population is a sign of recent star formation, not an ancient one. When those stars outline a spiral arm, they are marking places where gas was compressed and collapse followed not too long ago. In that sense, the blue light is a timing signal. It tells us the arm is not just a structural feature, but an active site in the life cycle of the disk. The pink regions add another layer. These are often H2 regions, clouds of ionized hydrogen surrounding hot young stars. Once a new massive star switches on, its ultraviolet radiation strips electrons from nearby hydrogen atoms, causing the surrounding gas to glow. That is why so many Hubble spiral galaxies show the same pairing, blue clusters and pink clouds. One marks the newborn or very young stellar population. The other marks the gas still being energized in the same neighborhood. When both sit along the arm together, they show that the arm is not simply a corridor of old stars, viewed at a favorable angle. It is a working zone where raw gas is being turned into starlight. Older theories often pictured spiral arms as fairly steady density wave patterns, and within that framework, the explanation of the brightness becomes especially elegant. Gas moving through the arm encounters a denser environment, experiences compression, and in some cases, a spiral shock. Annual Reviews notes that galactic shocks have long been considered a plausible trigger for the collapse of gas clouds and the resulting star formation along spiral arms. Elmer Green's review adds that gas can collapse into giant cloud complexes along the arms, aided by the local conditions there, including reduced shear and, in some treatments, the influence of magnetic fields aligned with the arm. So the arm can be understood as a site where several helpful factors come together: enhanced density, altered flow, stronger compression, and conditions that make gravitational collapse easier. Modern work has made the picture richer rather than simpler. Not every spiral galaxy appears to be governed by one long-lived stationary wave. Some arms may be transient, recurrent, strengthened by bars, or amplified by interactions with neighboring galaxies. But this does not weaken the main point of the present part. Whatever the larger origin of a given arm, gas compression inside spiral structure remains central to why the arms light up. The NED review on spiral structures in disk galaxies notes that simulations repeatedly show dynamic spiral arms forming in both stars and gas, along with molecular clouds and star formation developing within them. In other words, even when the arm is not treated as a perfectly steady wave, it still acts as a place where gas can gather and stars can be born. That helps explain why the arms can look so much sharper than the rest of the disk. The older stars in a spiral galaxy are distributed more broadly, often across the whole disk and bulge. Their combined light gives the galaxy much of its background glow. But when the arm is seeded with very luminous short-lived stars, plus ionized gas, plus dark dust tracing compressed lanes, the contrast rises quickly. The arm stops being only a mild overdensity and becomes the most visually active part of the galaxy. It is not that the rest of the disk is empty. It is that the arm is busy in a way the rest of the disk is not. There is also a subtle sequence built into the arm. Gas is compressed first. Dense molecular material develops. Star formation begins. Massive stars then illuminate the nearby gas and make the region stand out. Depending on the galaxy and the viewing angle, observers can sometimes trace offsets between dust lanes, molecular gas, H2 regions, and the youngest star clusters. That layered arrangement is one reason spiral arms have been so useful to astronomers. They are not merely shapes to classify. They preserve a record of how interstellar material moves through the disk and how new stars emerge from that motion. Interactions can strengthen the same effect. NASA's description of the colliding pair ARP 142 notes that gas and dust become compressed during the encounter, and that this compression triggers star formation visible as bluish knots along the distorted arms. This is useful because it shows the mechanism in a more dramatic setting. Even when an arm has been pulled or distorted by outside gravity, the immediate reason it lights up is still familiar. Gas is compressed, star formation follows, and the youngest stars mark the region in blue. The exact origin of the arm may differ, but the brightness still depends on what happens to the gas once the structure forms. Seen this way, the blue spiral arm is not simply a pretty curve in a telescope image. It is a narrow strip of the galaxy where motion, gravity, gas physics, and stellar evolution all become visible at once. The density enhancement helps gather gas. Compression helps destabilize that gas. New stars appear. The hottest among them flood the arm with blue light. Nearby hydrogen glows pink. What we call the brightness of the arm is therefore the visible outcome of a chain of physical events, not a mere decoration drawn over the disk. The arms are not the only structures capable of rearranging gas and reshaping orbits. In many spiral galaxies, a straight bar cuts across the inner region and changes how matter flows through the disk. That means the brightness of the arms may depend not only on the arms themselves, but also on a larger internal engine closer to the core, one capable of feeding structure farther out. Why do so many spiral galaxies hide a bar at their center? For several parts, the eye has been pulled outward toward the arms, the blue star clusters, the dust lanes, and the curved structure that makes a spiral galaxy so recognizable. Then the center starts to interfere with that simple view. In many disk galaxies, the core is not just a round bulge with arms curling away from it. A straight, elongated structure cuts across the middle, and the arms begin from its ends rather than from the nucleus itself. NASA describes a barred spiral as a galaxy with a lane of stars, gas, and dust slicing across its central region, and notes that both the Milky Way and Andromeda belong to this subtype. The same NASA overview adds that barred spirals make up about 2/3 of spiral galaxies. So the bar is not a small exception in galactic anatomy. It is one of the most common forms a mature spiral disk can take. Once that is seen clearly, the role of the center changes. The galaxy is no longer just a disk that happens to have arms. It is a system whose inner region can reorganize the motion of matter on a large scale. NASA's Hubble description of NGC 1000, 365 states this in unusually direct terms. The bar funnels material into the hub, triggers star formation, and feeds the bulge, while the spiral arms begin at both ends of the bar. That single arrangement already tells us something important. The bar is not decorative. It changes where gas goes, where stars are born, and how the inner galaxy grows. This is why the bar matters dynamically. A rotating galaxy does not merely hold matter in orbit. It also has to redistribute angular momentum. That phrase can sound abstract until the bar is brought into view. Reviews hosted by Ned describe bars as efficient agents of angular momentum transfer. As they exchange angular momentum with the disk and halo, they allow gas to flow inward, and that inflow can help build central structure over long timescales. In other words, the bar is one of the main ways a galaxy can rearrange itself from the inside without requiring a violent merger to do the job. That slow internal reshaping is one of the major themes of modern galaxy evolution. Astronomers often call it secular evolution, change that accumulates over many rotation periods through the galaxy's own internal dynamics rather than through a single catastrophic event. Kormendy's review at NED explains that bars are central to this process, and that barred spirals include cases where the arms start directly from the ends of the bar, and others where an inner ring links the bar to the arms. Either way, the message is the same. The central bar helps organize the flow of matter across the inner disk, and the outer spiral pattern is often tied to that organization. Images make this easier to hold in the mind. NGC 1300 is one of the clearest examples. A long central bar cuts through the galaxy's core, and two grand spiral arms peel away from its ends. NASA's description points out exactly this geometry, and also notes that the Milky Way is believed to be a barred spiral as well. NGC 685 shows the same basic logic in a different system, with feathery spiral arms sprouting from the ends of a central bar. The repetition of that design across many galaxies is what makes the bar so hard to dismiss. The structure recurs because it is a natural dynamical outcome in many rotating disks, not because a few galaxies happen to grow in unusual shapes. The Milky Way brings the subject much closer. We do not get an external face-on view of our own galaxy, so the bar had to be inferred indirectly for a long time from star counts, gas motions, and infrared surveys. NASA explains that infrared images from the Spitzer Space Telescope helped show that the Milky Way's spiral structure is dominated by two major arms wrapping off the ends of a central bar of stars. ESA has gone further with Gaia-era mapping, describing the Milky Way as a barred spiral galaxy, and noting that its central bulge has an elongated, peanut-like bar with a half-length of about 10,000 light-years. In 2019, ESA reported that Gaia data revealed the galactic bar in three-dimensional space based on geometric distance measurements, moving the picture beyond indirect hints. That observational history matters because it shows why bars can remain hidden in plain sight. Invisible light, dust obscures the inner Milky Way. Infrared sees deeper through that dust, and the underlying stellar structure becomes clearer. NASA's infrared view of NGC 253 makes the same point for another barred galaxy. Visible light is complicated by dark dust and bright young stars, but near-infrared reveals the full population of stars more clearly and exposes the bar running through the center. A bar is therefore not always hard to detect because it is weak. Sometimes it is hard to detect because the wrong wavelength emphasizes the surface clutter rather than the stellar backbone of the disk. Once the bar is visible, its effect on gas becomes one of the most useful clues to what it is doing. Bars create non-circular gravitational forces in the inner galaxy. Gas clouds responding to that potential do not simply orbit in neat circles. They can be torqued, shocked, and driven inward along dust lanes. NED's review on barred galaxies says theoretical studies suggest that large-scale stellar bars can be highly effective in delivering gas to the central few hundred parsecs of a spiral galaxy, where that gas may then trigger rapid star formation. NASA's material on NGC 1365 and Maffei 2 presents the same mechanism in observational language. Bars drive gas and dust into the center, and that inflow is linked to starbursts and bulge growth. This inward transport changes how the whole galaxy ages. If gas is steadily funneled toward the center, then the central region can keep building stars, growing denser, and in some cases feeding a central black hole. NED's review of rings and bars notes that inflowing gas can help build the bulge and drive evolution across morphological types, while nuclear rings in many barred systems turn significant amounts of gas into stars. So the bar is connected not only to the shape of the disk, but also to the long-term growth of the inner galaxy. A barred spiral is a galaxy whose central architecture is still doing work. That also explains why the bar and the arms are so often linked rather than competing features. The bar can seed or strengthen spiral structure farther out by changing orbital families and by feeding gas into the regions where arms take shape. In some barred spirals, the arms begin right at the ends of the bar. In others, a ring forms first, and the arms start from that ring. Kormendy's classification summary emphasizes both arrangements, which means the outer pattern can be connected to the central bar in more than one geometrical way. The core idea remains consistent. The bar helps determine how material and structure are organized across a substantial fraction of the disk. A useful way to think about the bar is to stop treating the center as a resting place. In a spiral galaxy without this perspective, the eye imagines the core as the fixed hub and the arms as the active parts. But barred spirals show that the hub itself can be a region of transport. Stars stream through elongated orbital families. Gas loses angular momentum and moves inward. Dust lanes mark compressed flows. Fresh star formation can ignite where inflowing material piles up. The center is not passively holding the galaxy together. It is helping rewrite the internal map. There is another reason bars matter for the bigger timeline of the universe. NASA's Hubble report from 2008 found that barred spirals were much rarer earlier in cosmic history, and that the fraction of spiral galaxies with bars has grown over time. That result suggested bars are latecomers on average, appearing more often as disks settle and mature. NASA's current galaxy types overview still reflects that interpretation, noting that scientists think the presence of a bar indicates a galaxy has reached full maturity. The wording should not be taken as a hard rule for every individual system, but it captures an important trend. A bar is often a sign that the disk has evolved enough for internal dynamical instabilities to become organized on a large scale. By this point, the bar no longer looks like a simple straight feature laid across a spiral by accident. It is a dynamical engine. It can redirect gas, reshape orbits, alter where stars form, and help connect the central galaxy to the outer arms. That is why so many spirals hide a bar at their center. A rotating disk is not trying to remain geometrically simple. Over time, it develops structures that move angular momentum around and reorganize matter. The bar is one of the clearest results of that internal evolution. Not every spiral pattern has to be produced by internal structure alone. A nearby companion can tug on the disk, pull out asymmetries, and amplify arms across tens of thousands of light years. In some galaxies, what looks like graceful design may also be the long memory of an earlier gravitational encounter. Were some spiral arms triggered by a passing galaxy? A spiral galaxy can look so balanced that it invites the wrong assumption. The arms seem to belong entirely to the galaxy itself, as though they rose from the disk through internal motion alone and remained there because the system had found a stable design. Then, a companion enters the frame. A smaller galaxy hangs near one arm, or crosses above the disk, or leaves a distorted outer edge that no clean textbook sketch can hide. At that point, the center of the subject shifts. Some spiral structure is not only the result of what a galaxy does to itself, it can also be the visible record of what another galaxy once did to it. This possibility became much more concrete in the early 1970s, when Ala Toumre and Juri Toumre showed that close galactic encounters could reproduce bridges, tails, and large-scale distortions using gravitational simulations. Later reviews at NED described that result as a turning point. Close passages can deform disks and generate the sort of tidal structures astronomers actually observe. That matters here because the same gravitational disturbance that pulls out tails and bridges can also amplify spiral structure inside the disk. In other words, a passing galaxy does not need to tear a spiral apart in order to leave a signature. It can strengthen the very pattern that makes the galaxy look orderly from a distance. The physics begins with a simple asymmetry. Gravity from a nearby companion does not pull equally on every part of the disk at the same moment. The near side and the far side feel different forces. The outer disk, being more loosely bound than the dense inner region, is especially vulnerable. Once that uneven pull acts across a rotating disk, the response is not just a general wobble. Material is displaced. Orbits are stretched. Density rises along some lanes and falls along others. The companion can therefore act like an external amplifier, taking a disk that might otherwise look modestly structured and helping it develop strong, large-scale spiral arms. Messier 51 is the classic case because it looks almost too perfect. The Whirlpool galaxy sits about 31 million light-years away, and its two sweeping arms are among the clearest grand design spirals in the sky. Yet one of its most important features is not the arm itself, but the companion galaxy at the end of one arm, NGC 5195. NASA's Hubble material on M51 repeatedly emphasizes that pairing. The famous spiral is not an isolated pattern floating in empty space. It is part of an interacting system, and theoretical studies discussed in NED reviews note that tidal interaction models have been used specifically to reproduce M51's inner spiral structure. That is a powerful shift in interpretation. Instead of treating M51 as the example of a spiral that simply formed itself in perfect symmetry, astronomers can read it as a disk whose beauty has been strengthened by an encounter. The companion has not merely arrived beside the pattern by coincidence. It may be part of the reason the pattern became so pronounced. NED's review of interacting galaxy dynamics states this directly. Perturbations strong enough to generate the large-scale tidal features in systems like M51 also give rise to a grand design spiral density wave in the inner disk. That means the same gravitational event can shape the outskirts and organize the interior at the same time. NASA's Hubble page on ESO 550-2 describes a pair of spiral galaxies in which tidal interaction from the smaller companion has clearly deformed one arm of the larger galaxy. The page also notes strong star formation in that distorted arm and in a ring around the core. This is exactly the kind of evidence that keeps the external trigger picture strong. The arm is not merely bent. The disturbance has also affected the gas enough to help stimulate new stellar birth. A close passage can therefore reshape the geometry and alter the disk's internal activity at the same time. NGC 2000, 207, and IC 2000 163 make the same lesson even harder to ignore because the system is so visibly unsettled. NASA's Hubble description explains that strong tidal forces from NGC 2207 have distorted IC 2163, flinging stars and gas into streamers stretching about 100,000 light-years. APOD's summary of the pair adds more detail. Tides of matter, sheets of shocked gas, dark dust lanes, bursts of star formation, and streams of cast-away stars are all part of the interaction. When a pair like this is seen in detail, the phrase "passing galaxy" stops sounding mild. A close encounter can reorganize huge regions of a disk and leave marks that remain visible over distances far larger than any single stellar nursery. What makes these interactions so useful scientifically is that they join two scales that are often discussed separately. On the large scale, the encounter reshapes orbits and produces tidal arms, tails, bridges, and lopsided outer disks. On the local scale, the same disturbance compresses gas, rearranges dust lanes, and can increase star formation in selected regions. ESA's Hubble material on interacting systems makes this connection explicit, noting that gravitational interactions pull neat spiral forms out of shape, while the disruption to gas clouds triggers vigorous star formation. So the visible aftermath is not only a matter of geometry. It is also a record of gas physics responding to new gravitational conditions. This is also where the word fossil becomes useful, as long as it is handled carefully. A tidal spiral arm is not a fossil in the literal sense of something mineralized and inert. It is a fossil in the dynamical sense, a present-day structure that preserves evidence of an earlier event. A galaxy can carry that memory for a long time because galactic timescales are vast. Material set into altered orbits by an encounter does not immediately forget what happened. The disk continues to respond, the spiral can persist or recur, and star formation can light up the disturbed lanes long after the closest approach itself has passed. This helps explain why not all grand design spirals should be interpreted the same way. Some may be linked mainly to internal structures such as bars. Some may reflect large-scale patterns that evolve within the disk. Others may owe much of their present appearance to a companion's pull. The NED Dawes review on spiral structures states this plainly. Many unbarred grand design spirals are associated with tidal interactions, while other spiral forms may arise from different processes. That keeps the field honest. The sky contains one family of shapes, but not one single recipe. There is also a useful historical contrast here. Earlier in the story of spiral structure, a lot of attention was directed toward explaining how a galaxy could maintain arms internally despite differential rotation. That remains an important line of work. But tidal interaction studies expanded the landscape by showing that a companion could excite a large-scale spiral response without requiring the disk to do all the work alone. The result was not the replacement of one theory by another, but a broader understanding. Galaxies live in environments, and those environments can matter strongly for morphology. The visual evidence for this is often strongest in the outer disk. Outer arms are less tightly bound and more easily stretched. A companion can pull one side harder, producing asymmetry that would be difficult to attribute to a purely internal, perfectly balanced mechanism. In some systems, the result is a bridge toward the companion. In others, it is a long tail trailing away. In still others, one arm looks unusually extended, bright, or deformed, while the rest of the galaxy tries to maintain a more familiar spiral appearance. These details are exactly the sort of clues astronomers use when they try to reconstruct past encounters from present structure. A close encounter does not have to end in an immediate merger to matter. Even a grazing passage can be enough. NASA's material on NGC 2000, 207 and IC 2000, 163 describes the event as a grazing encounter, yet the visible consequences are extensive: streamers, distorted shapes, compressed gas, and strong star formation. That is an important reminder because it means the trigger for a spiral response does not always require the most extreme possible collision. A near pass at the right geometry and relative speed can leave a major imprint on the disk. Seen from this angle, a spiral arm becomes more than a pleasing curve of stars and dust. In some galaxies, it is also a historical document. The arm may tell us that another galaxy came close, pulled unevenly across the disk, lifted material into new paths, and helped organize the visible pattern that remains. That is why the shape of a galaxy can preserve the memory of disturbance across tens of thousands of light years. The structure is present now, but part of its cause may belong to an encounter long past. A companion can amplify structure we can see, but the stars and gas we can see are not enough to explain how fast galaxies rotate in the first place. The spiral is shaped by visible matter, by encounters, and also by a larger unseen mass component surrounding the disk. Is dark matter quietly holding the spiral together? By this point, the spiral galaxy has already become harder to read than it first appeared. The arms are not simple painted ribbons. Gas moves through them, stars are born inside them, bars can reorganize the inner disk, and nearby companions can strengthen or distort the whole pattern. Then the subject widens again, because even after all of that, the visible galaxy still does not seem to contain enough mass to explain how it rotates. That is where dark matter enters the story, not as a decorative extra, but as one of the main reasons spiral galaxies behave the way they do. The basic evidence comes from rotation curves. A rotation curve is a measurement of orbital speed as a function of distance from the galactic center. Astronomers build these curves from Doppler shifts in starlight, and very importantly, from the 21-centimeter radio emission of neutral hydrogen gas, which can be traced far beyond the bright optical disk. If most of a spiral galaxy's mass were concentrated where most of its light is concentrated, then the outer parts should orbit more slowly as distance increases, much as planets farther from the Sun move more slowly than planets closer in. But that is not what astronomers found. In many spirals, the rotation curve stays roughly flat far beyond the bright stellar regions, meaning the outer material keeps moving faster than the visible mass alone can easily account for. That flatness changed galaxy astronomy. The review by Yoshiaki Sofu and Vera Rubin at NED states the standard inference very plainly. Flat rotation curves are interpreted as evidence for a massive dark halo surrounding the spiral disk. The same review notes that by the 1970s, observations had established that many spiral galaxies did not show the expected strong decline in orbital speed at large radii. This was not a small correction to earlier expectations. It meant that a large fraction of galactic mass was not following the light. Vera Rubin's work became central because she and Kent Ford helped turn this from a suspicion into a durable observational result. The American Astronomical Society summarizes their finding in straightforward terms. Stars at the edge of a spiral galaxy travel as fast as those nearer the center, rather than slowing the way a simple visible mass model would predict. Carnegie Science's recent summary of Rubin's legacy says the same thing and highlights her famous conclusion from a 1980 paper. The conclusion is inescapable that non-luminous matter exists beyond the optical galaxy. That sentence matters because it does not overstate what was known. It does not claim the nature of the unseen mass had been solved. It states that the luminous galaxy was not enough. Her shorter line fits this part especially well. What you see in a spiral galaxy is not what you get. That line works because spiral galaxies are so visually convincing. The glowing disk, the dust lanes, the blue arms, the central bulge, all of it encourages the eye to think the important mass has already been shown. But the rotation curve says otherwise. The visible galaxy is only part of the gravitational system. Surrounding the bright disk is an extended halo whose presence is inferred from motion rather than light. NASA's current dark matter overview explains the broader principle in similar language. Astronomers map unseen mass by observing how gravity affects visible objects. This does not mean dark matter is simply holding the spiral together in the casual sense of gluing the arms into place. The idea needs to be stated more carefully. Dark matter is thought to dominate the galaxy's mass budget on large scales, especially in the outer halo, and that changes the gravitational field in which the disk rotates. Because the disk is embedded in that deeper potential, the speeds of stars and gas do not fall off the way they would if only the luminous matter were present. NED reviews on dark matter in galaxies note that the outer parts of spirals are halo-dominated, and that the mass profile inferred from rotation curves extends well beyond the bright optical disk. That wider gravitational framework matters for spiral structure because the disk does not evolve in isolation. The stars, gas, bar, and arms all live inside the larger mass distribution of the galaxy. If the halo were absent, or if the total mass were much smaller, the orbital speeds, stability conditions, and response of the disk to disturbances would all be different. A spiral arm may still be a density pattern, a transient recurrent feature, a bar-linked structure, or a tidal response to a companion, but all of those processes unfold inside a potential shaped strongly by matter we cannot see directly. There is a useful observational contrast here between what light traces and what motion traces. Light is excellent at showing where stars are bright, where gas is ionized, where dust blocks the background, and where recent star formation is active. Motion does something different. Motion reveals enclosed mass. When outer hydrogen clouds or stars move faster than the visible galaxy can easily support, the orbit itself becomes evidence for a larger hidden mass distribution. That is why rotation curves became so decisive. They did not merely show that something odd was happening at the edge of galaxies. They measured the gravitational demand of the orbit directly. The Milky Way participates in the same story. NED's review on rotation and mass in the Milky Way and spiral galaxies states that the Milky Way, like Andromeda, is surrounded by a dark matter halo, and that rotation curves remain one of the main tools for estimating the galaxy's dynamical mass. ESA's Gaia-related material also frames the Milky Way rotation curve as a measurement of circular speed as a function of distance from the galactic center. Our own galaxy is therefore not an exception admired from the inside. It is one of the systems through which the same dark halo logic has been worked out. Spiral structure is made from ordinary matter, stars, gas, dust, and the forces shaping their motion. But the stage on which that structure evolves appears to be dominated by a non-luminous component. Carnegie Science summarizes Rubin's legacy by noting that dark matter makes up the overwhelming majority of a galaxy's mass in many discussions of spiral dynamics. Exact fractions vary depending on radius and model, but the central point is stable. The luminous disk is not the whole mass of the galaxy. That also explains why dark matter enters any serious account of how spirals persist and evolve. A disk embedded in a massive halo does not respond to perturbations the same way a disk made only of visible matter would respond. The halo affects orbital speeds, stabilizes or destabilizes certain modes depending on circumstances, and shapes how bars, spiral features, and encounters play out over long timescales. The review literature is careful here. Dark matter is not presented as a single, simple answer to every visible feature in a spiral galaxy. It is presented as an essential part of the gravitational framework within which all those visible features arise. There is another reason this part matters in the overall arc of the story. Earlier sections could still tempt the mind into thinking that spiral structure is mainly a problem of geometry and gas flow. Once dark matter is included, the scale changes. The glowing galaxy is no longer the full object. It is the bright inner tracer of a much larger mass distribution. What looks like a pattern of light is moving inside a halo that does not announce itself through color, dust lanes, or Hubble photographs. It announces itself through gravity. That is why Rubin's line remains so effective. It is not memorable only because it is concise. It is memorable because it captures the central mismatch between appearance and dynamics. A spiral galaxy looks luminous, structured, and understandable at first glance. Then the rotation curve shows that the visible part is not enough, and the galaxy becomes a layered system whose dominant mass is inferred rather than seen. By now, the spiral has become a much more demanding object than it seemed at the beginning. The arms are not permanent material ribbons. Gas compression explains why they light up with young blue stars. Bars redistribute matter through the center. Companions can amplify the pattern from outside. And beyond the visible disk, an extended dark halo helps determine how the whole system rotates. The result is not a prettier version of the old picture. It is a more complete one. Spiral structure belongs to the stars we see, the gas we can map, the disturbances we can model, and the unseen mass required by orbital motion. Some spirals carry long, clean, almost textbook arms, while others look patchy, broken, or nearly without arms at all. That unevenness means one more layer of the subject is still waiting. If the underlying physics is so widespread, why do spiral galaxies not all build the same visible design? By now, it would be easy to expect a simple rule. A disk rotates. Gas moves through denser lanes. Stars form along those lanes. A spiral appears. But the sky does not settle into that neat expectation. Some galaxies display two long, clean, high-contrast arms that can be traced far from the center. Others look broken into short segments, patches, and feathery fragments. A few disks look so weakly patterned that the spiral seems almost unfinished. This contrast is built directly into modern descriptions of spiral structure. Grand design spirals tend to show long, continuous, often two-armed patterns, while flocculent spirals are patchy and discontinuous. The difference is not just a matter of prettier versus messier. It reflects different balances between gas, stars, internal instabilities, bars, and environmental history. Claire Dobbs and Junichi Baba's review on spiral structures in disk galaxies states that the flocculent or grand design nature of a galaxy is directly linked to the mechanism generating the spiral arms. The same review lists several major pathways: quasi-stationary density, wave ideas, local instabilities that are swing amplified, tidal interactions, and bars that can help drive arms. That means one visible family of shapes is being produced by more than one physical root. The language astronomers use here is quite revealing. A grand design spiral usually means the pattern is global. The two dominant arms are long enough, regular enough, and bright enough that the eye can follow them across much of the disk. In contrast, a flocculent spiral is built from smaller pieces. Ronald Buta's Morphology Review describes flocculent galaxies as lacking strong two-armed symmetry and instead showing spiral-like structure made of small pieces of arms. ESA Hubble says the same thing in much simpler visual language for NGC 4237, the cotton wool galaxy. Its spiral arms are patchy and discontinuous rather than clearly distinguishable from one another. That visual contrast can be misleading if it is read too quickly. A ragged galaxy is not a failed spiral. It is still a disk responding to gravity, orbital shear, and star formation, but it may be organizing structure on more local scales rather than through one dominant global pattern. Dobbs and Baba note that local instabilities are often associated with flocculent or multi-armed galaxies, whereas grand design systems are more often connected with tidal interactions, bars, or long-lived, large-scale patterns. So the difference is not that one type follows physics and the other does not. The difference is that the physics is being expressed at different scales and with different degrees of coherence. Gas supply is one of the main reasons this varies. Spiral structure becomes much more visible when a disk contains enough cold gas for compression, cloud formation, and new stars to mark out the lanes. Kenneth Kennicott's review on star formation along the Hubble sequence notes that grand design spirals show strong local enhancements of star formation in their arms, but this does not necessarily mean a higher total star formation rate for the whole galaxy. That distinction is important. A grand design spiral can look dramatically more organized because the star formation is concentrated along a strong pattern, while a flocculent spiral may spread its activity among many smaller segments. The total amount of star formation is not the whole story. Where that star formation is concentrated matters just as much for appearance. Old stars and young stars can also tell slightly different stories inside the same galaxy. Dobbs and Baba discuss work suggesting that both grand design and flocculent spirals may show broadly similar structure in the gas and young stars, even when the underlying old stellar population looks different. They also note that in some cases, an apparently grand design galaxy may hide a more flocculent underlying pattern in older stars or molecular gas. This means the galaxy's classification can depend partly on which component is being emphasized and at what wavelength it is observed. A spiral that looks broken in visible light can look more coherent at longer wavelengths, if dust effects are reduced and the older stellar disk becomes clearer. That wavelength dependence is one reason morphology is not always as straightforward as a quick photograph suggests. Ronald Buter notes that the appearance of a flocculent spiral can be strongly affected by dust, and that at longer wavelengths, such a galaxy may appear more grand design. This is a useful correction because it prevents a common mistake. A galaxy is not changing its nature when viewed in infrared instead of visible light. The observations are simply tracing different ingredients with different clarity. Visible light often emphasizes bright young stars and dark dust structure. Infrared is better at revealing the broader stellar backbone through obscuring dust. Bars add another major difference. In several earlier parts, the bar has already emerged as a powerful internal engine capable of redistributing angular momentum and channeling gas through the inner disk. The same NED review on spiral structures says bars may play a role in inducing spiral arms, and it treats barred galaxies as a somewhat special case within the broader picture of spiral generation. This helps explain why some galaxies show clean, strong arms that seem to launch from the ends of a bar. In those systems, the bar is not a side feature. It can help impose a large-scale order on the disk and strengthen a dominant two-armed pattern. Tidal history matters just as much. Some galaxies look highly organized not because they are more isolated, but because an encounter has amplified their spiral structure. Dobbs and Barber explicitly connect many unbarred grand design spirals with tidal interactions. In a different review, Curtis Struck notes that before mergers, star formation is often concentrated in spiral waves or bars, and tidal tails can look like extensions of the spirals themselves. A galaxy's present symmetry can therefore carry the memory of a past disturbance. A clean grand design pattern may sometimes be the visible consequence of a companion's pull, rather than the product of a fully self-contained internal mechanism. Flocculent spirals point in a different direction. The same review literature connects them more naturally with local instabilities, short-arm segments, and recurrent features shaped by the ordinary instability of the disk, rather than one dominant long-range organizer. Dobbs and Barber also remark that self-propagating star formation can produce a much more irregular and flocculent appearance in gas and young stars, even if that mechanism by itself is not now treated as the full answer to spiral structure. This is why a patchy spiral can look almost shredded without being dynamically trivial. The disk is still active, still forming stars, still being sheared by differential rotation, but the visible structure is being built from many local episodes instead of one clear global arm pattern. There is also a classification issue hidden inside this discussion. The familiar Hubble sequence tells us whether a galaxy is spiral, barred spiral, elliptical, lenticular, and so on, but it does not fully capture the arm style itself. Buter points out that grand design and flocculent structure are not directly built into the original Hubble classification. That matters because two galaxies can both be called spirals and still differ strongly in how their arms are organized. The coarse category tells us the galaxy has a disk and spiral structure. The finer arm class tells us how coherent, symmetric, and extended that structure really is. A good visual pair makes the contrast easier to hold. ESA, Hubble's NGC 5643, is described as a grand design spiral, with two large winding arms clearly visible, defined by bright blue stars, dust clouds, and pink star-forming regions. NGC 4237, by contrast, is presented as flocculent, with patchy, discontinuous arms that give it a cotton wool appearance. Those two galaxies are useful not because they represent the only two possibilities, but because they show the ends of a spectrum. Many real disk galaxies sit somewhere between them, mixing bits of strong symmetry with shorter broken segments. The older literature sometimes encouraged the hope that one mechanism would explain all of this cleanly. Modern work has moved in a different direction. Dobbs and Barber's review emphasizes that the proposed mechanisms are not necessarily mutually exclusive. A bar can help drive arms. A tidal interaction can trigger or strengthen a wave. Local instabilities can build shorter features even within galaxies that also show a stronger global mode. That mixed picture is one reason the sky refuses to settle into one template. The spiral galaxy is not one machine repeating one design. It is a family of rotating disks responding to similar physical rules under different initial conditions and different histories. So why do some galaxies have perfect arms while others look ragged? Because visible spiral form depends on more than rotation alone. It depends on whether the disk has enough gas to make compression visible, whether star formation is concentrated or scattered, whether a bar is helping impose large-scale order, whether a companion has amplified the pattern, how the old stellar disk is arranged underneath the young stars, and how the system has evolved over time. A spiral galaxy can therefore be grand design, flocculent, mixed, multi-armed, or nearly armless without abandoning the same broad framework of disk dynamics. The difference is in how strongly the pattern is organized, how long it persists, and which mechanism is doing the most work in that particular galaxy. It is easy to classify a spiral galaxy when it is far away and facing us. It is much harder to do the same thing for the galaxy we live inside. The Milky Way does not present itself as a full photograph. It has to be reconstructed from fragments, dust-obscured views, radio maps, infrared surveys, and stellar distances, all while we remain trapped within the disk whose shape we are trying to understand. It is easy to call a distant galaxy spiral when the whole pattern lies open in a telescope image. Two arms, a central bulge, perhaps a bar, dust lanes crossing the disk, blue star-forming regions tracing the structure. The Milky Way gave astronomers no such advantage. We live inside its disk, surrounded by stars, cut across by dust, and limited to a side-on view from one small location about 26,000 light-years from the galactic center, roughly 8 kiloparsecs. From that position, the galaxy does not present itself as a finished photograph. It has to be rebuilt from direction, distance, velocity, and inference. The first major correction came before anyone could map the spiral arms at all. In the early 20th century, Harlow Shapley used RR Lyrae stars in globular clusters to estimate distances and realized that the clusters were not centered on the Sun. They were distributed around a point far away in the direction of Sagittarius. NASA's historical summaries note that by studying the distribution of globular clusters and measuring their distances, Shapley was able to infer the location of the center of the Milky Way and the Sun's offset from it. That changed the scale of the subject immediately. The solar system was not near the middle of the galaxy. It was living out in the disk. That result was foundational, but it still did not reveal the Milky Way's full shape. Visible light could not carry the job by itself because the galactic plane is crowded with dust. Dust absorbs and scatters starlight, especially at shorter wavelengths. So the farther astronomers looked through the disk, the more the picture broke apart. The obstacle was not lack of interest. It was the medium itself. We were trying to sketch a city while standing inside its foggiest avenue. To move forward, astronomy had to switch wavelengths. Radio astronomy opened the next door. Neutral hydrogen in the galaxy emits radiation at a wavelength of 21 centimeters, a signal that can pass through dust far more effectively than visible light. NASA explains that this line is especially useful for mapping the disk portion of our galaxy, while other radio tracers such as carbon monoxide help reveal molecular clouds concentrated in spiral arms. That changed the kind of map astronomers could build. Instead of relying only on starlight, they could trace the gas itself, the raw material spread through the disk and organized into large-scale structure. This was an enormous step, but it came with its own difficulty. A radio telescope can detect hydrogen clouds in many directions, yet turning those detections into a three-dimensional map requires more than seeing where the gas lies on the sky. It also requires distance. Velocities from Doppler shifts helped, especially when combined with models of galactic rotation. But velocity alone does not always tell you uniquely where an object sits along the line of sight. That is why Milky Way mapping remained uncertain for decades. Astronomers could see evidence of spiral structure, but the exact number of arms, their positions, and even the detailed role of the central bar remained under debate. Infrared observations helped again by piercing deeper through the dust. In 2008, results from NASA's Spitzer Space Telescope argued that the Milky Way has two major stellar arms, Scutum Centaurus and Perseus, connected to the ends of a central bar, while the Sagittarius and Norma features appear less prominent as stellar arms. NASA and JPL described this as a makeover of our view of the galaxy. It was a useful reminder that the answer depended strongly on which component was being traced. Gas, young stars and older stars do not always outline the same pattern with equal strength. Then came one of the most decisive tools of all: direct parallax measurements across the galaxy. The Very Long Baseline Array and the Bar and Spiral Structure Legacy Survey measured trigonometric parallaxes and proper motions of masers in high-mass star-forming regions. Those masers act like precise radio signposts, anchored to places where spiral structure is actively forming stars. NRAO reports that more than 100 such parallaxes and proper motions had already provided strong evidence for the existence of spiral arms, accurately locating many arm segments and measuring spiral pitch angles ranging from 7 to 20 degrees. This mattered because parallax is geometry, not guesswork. It gave astronomy a direct way to place major star-forming regions in three-dimensional galactic space. That is the point where the phrase "inside the trap" becomes fully deserved. We are not trapped by ignorance alone. We are trapped by viewpoint. A face-on galaxy gives morphology almost immediately. An embedded observer gets only slices, velocities, obscuration, and partial distances. So the Milky Way had to be assembled in layers: globular clusters to find the center, radiohydrogen to trace the disk, carbon monoxide, and H2 regions to mark star-forming arms, infrared surveys to expose the stellar bar, and parallax to anchor key features with direct distances. Gaia added another level of refinement. ESA describes Gaia as a mission to build the most precise three-dimensional map of the Milky Way by surveying more than 1 billion stars. In 2019, ESA reported the first direct measurement of the Milky Way's bar by combining Gaia data with complementary observations, and by 2025 ESA's Gaia summaries were stating that the galaxy has more than 2 spiral arms and that the arms are less prominent than astronomers had once thought. That is important because it shows the picture is still being sharpened. The Milky Way is securely a barred spiral galaxy, but the exact strength, continuity, and prominence of its arms are not frozen in one old diagram from a textbook wall chart. This is where the human side of the science becomes especially strong. No one ever stepped outside the Milky Way to take its portrait. Every improvement came from making better use of fragments. A variable star here, a hydrogen line there, a dust-penetrating infrared survey, a maser distance measured with radio interferometry, a billion-star astrometric catalogue from space. The galaxy had to be reconstructed the way a large terrain is reconstructed in darkness by careful measurements taken from inside the landscape itself. The result is not merely a cartographic success. It changes how the subject feels. When Carl Sagan said, "We are made of star stuff," he was not making a decorative remark about astronomy. NASA still cites that line when explaining that the heavier atoms essential for life were forged in stars and stellar processes. In the context of the Milky Way, the line lands with particular force because the spiral structure is not just something we observe from outside. Our sun, our planets, our chemistry, and our own bodies belong to one small region of that larger galactic architecture. So how did we learn the Milky Way is spiral from inside the trap? Not by one image and not by one method. We learned it by combining distance indicators, gas tracers, infrared penetration through dust, precision radio astrometry, and enormous stellar maps until the fragments converged on a consistent picture. A barred spiral galaxy with the sun living well out in the disk, far from the center, inside a structure far larger than early observers imagined. That answer carries a special weight because it was earned from one of the worst possible viewing positions for the task. We did not inherit the map. We extracted it. When the Milky Way is no longer an abstract band of light, but a barred spiral system reconstructed from evidence, the ending changes shape as well. Spiral arms stop looking like fixed architecture laid down once and kept forever. They begin to look like patterns maintained, rebuilt, sharpened, or weakened over time by gravity, gas, bars, and encounters. That final turn is where the full subject settles, not into a frozen design, but into a restless one that keeps writing itself. Are spiral arms ancient architecture or patterns that keep rewriting themselves? By the time a spiral galaxy has been followed from its bright blue arms to its gas lanes, from its bar to its dark halo, from its companions to its buried structure inside the Milky Way, the old picture is no longer enough. The spiral cannot be treated as fixed architecture in the ordinary sense, as though a galaxy built its arms once and then carried them unchanged across cosmic time. What the evidence supports instead is more dynamic and more demanding. Spiral arms are patterns that can persist for a while, strengthen, weaken, shift, recur, and in some galaxies be renewed by more than one physical process. The galaxy does not simply keep its shape. It keeps working on it. This is one of the strongest conclusions to come out of modern work on spiral structure. Reviews of disk galaxy dynamics no longer treat all spiral arms as one single kind of object with one single lifetime. Some grand design spirals appear strongly linked to bars or tidal interactions. Some patterns behave more like recurrent features in a self-gravitating disk. Some arm segments are more local and fragmented. That does not make the subject weaker. It makes it more realistic. The visible arm is not a monument. It is a response. The reason this matters is that the arm is built inside a moving system where almost everything important is in motion at once. Stars orbit through the disk. Gas clouds compress and break apart. New stars appear, and the most massive among them burn fast and fade from the scene quickly by galactic standards. Bars can redirect gas inward. Companions can pull from outside. The dark halo continues shaping the overall gravitational field. In a system like that, a spiral arm is best understood not as a rigid, decorative feature, but as organized behavior emerging inside a restless disk. That is why the old language of permanence has to be handled with care. A spiral galaxy can preserve a recognizable form for a long interval, but that does not mean the same stars remain locked inside the same arm forever. Earlier parts of this series already showed why the winding problem makes that unlikely for most spirals. The stronger modern view is that the pattern can outlast the membership. The visible arm can remain meaningful while the material within it changes. Just as gas flows in, star formation rises, and stellar populations age and move on. The arm survives as organization, not as fixed inventory. Recent Milky Way work has pushed this point even further. ESA's Gaia team has said that the Milky Way has more than 2 spiral arms, and that those arms are less prominent than astronomers once thought. In August 2025, ESA also reported that young star clusters are unevenly distributed through the Milky Way's arms, and that this pattern implies the arms are likely transient rather than long-lived in a rigid sense. That is an important development because it takes the idea of evolving spiral structure and brings it home to our own galaxy. The Milky Way is not encouraging us to imagine a fixed pinwheel frozen in space. It is pointing toward a disk whose large-scale pattern changes over time. At the same time, galaxies do show enough continuity that the word temporary also has to be used carefully. Temporary on galactic timescales does not mean brief in any human sense. A pattern can last for many tens or hundreds of millions of years and still count as evolving rather than permanent. One orbit of the Sun around the Milky Way takes roughly 240 million years. So even a spiral feature that persists for only a modest number of galactic rotations can remain in place far longer than human civilization has existed. The galaxy can therefore be dynamic without looking chaotic, and changing without looking unstable to a human observer. Bars fit naturally into this ending because they are part of the same larger story of internal change. NASA's Galaxy Evolution Overview says scientists think stellar bars are temporary structures that form when stars, gas, and dust at the base of spiral arms build up into a denser region that favors star formation. That means even one of the most striking central features of a mature spiral galaxy is being treated not as timeless architecture, but as a structure that can emerge during evolution. Once the bar is allowed to evolve, the old desire to treat the whole galaxy as fixed geometry becomes even harder to defend. Interactions say the same thing from another direction. Webb and Hubble images of interacting galaxies show spiral arms being stretched, unwound, distorted, or reorganized by encounters. NASA's 2024 web release on ARP-107 describes a galaxy that likely had the shape of a spiral before the interaction and now shows arms reshaped into a new outline after the encounter. A galaxy like that makes the central point almost unavoidable. Spiral structure is not only something a galaxy possesses, it is something a galaxy can have modified. The visible form can carry the memory of past gravity. This is where the subject becomes wider than morphology. A spiral arm is not only a line on a classification chart. It is where orbital mechanics, gas physics, star formation, and galactic history overlap in a way we can actually observe. The arm brightens because gas is compressed and hot young stars appear. It persists because the disk can sustain or rebuild organized patterns. It shifts because the galaxy is not rotating like a solid wheel. It may strengthen because a bar channels matter or a nearby galaxy amplifies the response. It may weaken because the local conditions that supported it do not last forever. So the strongest ending is not the neatest one. The strongest ending is the one that leaves the galaxy alive in the physical sense. Spiral arms are not best described as ancient decorations attached once to a finished disk. They are better described as evolving patterns shaped by gravity, gas, bars, encounters, and the deeper mass distribution of the system. Some may last longer than others. Some may be rebuilt more than once. Some may owe their present form to internal dynamics, some to outside disturbances, and many to a combination of both. That answer is satisfying for a deeper reason as well. It allows beauty and mechanism to remain in the same frame. The curved arm in a telescope image is still beautiful, but its beauty does not come from being untouchable or eternally fixed. It comes from the fact that order can arise inside motion, that a disk full of stars and gas can keep producing recognizable form without ever becoming static, and that large-scale structure can be visible evidence of processes still unfolding. In that sense, every spiral galaxy is carrying two stories at once. One is the story the eye sees immediately: sweeping arms, bright blue knots, dark lanes, a core holding the whole design together. The other is the story physics has had to uncover step by step: differential rotation, density enhancements, gas compression, bar-driven inflow, tidal forcing, and unseen mass inferred from motion. The full meaning of the spiral only appears when both stories are allowed to sit together. A line often attributed to Edwin Hubble fits well here. Equipped with his five senses, man explores the universe around him and calls the adventure science. It fits because the long effort to understand spiral galaxies has followed exactly that path. Astronomers began with appearance. Then they measured light, dust, gas, motion, distance, and time. Each step removed one more easy assumption. What remained at the end was not a smaller universe, but a more exact one. The spiral galaxy did not become less impressive when it stopped being a fixed wheel. It became more impressive because its order turned out to be dynamic. And that is where this journey comes to rest. Not in the claim that the mystery is finished, because it is not. Not in the claim that one mechanism explains every arm, because it does not. But in something firmer than that. The spiral arms of galaxies are real, measurable structures, and the best evidence we have says they are evolving patterns inside changing systems rather than rigid ornaments fixed for all time. The galaxy keeps turning. Gas keeps gathering. Stars keep appearing. Gravity keeps reorganizing the disk. And the pattern keeps being written again. If you have stayed with this long journey through spiral galaxies, thank you for being here. Your time, your attention, and your presence mean more than a number on a screen. A like or a soft tap on subscribe is a real encouragement for me to keep building these science stories with care. And if you want to leave a note, I would love to know where you are listening from, what time of day or night this found you, and what parts of the series you would like me to improve. Your thoughts help shape what comes next. I hope this part of the universe keeps you company in a good way tonight. Sleep well, and thank you for traveling through the Milky Way and beyond with me.